Well, it looks like it's time. Welcome back, everyone. So we are now on this week here. It's week 11 out of a 16-week semester, and we're turning the page to a brand new chapter. We're in chapter 4, looking at applications of the derivative. We're not going to cover all of chapter 4, just enough to get a good repertoire of different things we can do with that derivative. And after that, we'll be moving into chapter 5, turning towards integration. But any questions at all, folks, to start us out today? Any questions on the last material, the logarithms or exponential growth and decay? Okay, well, let's get started. Chapter 4 is a pretty interesting and wild ride, but it starts off pretty gentle, maximum and minimum values. But just to give a hint on where we're going, this is what chapter 4 is kind of all about. Let's scroll up to about here. If you want to go all the way to 3.1. And in 3.1, we said that the derivative itself is equal to the slope of the tangent line given curve. So using that idea, we were able to next start, I think this is in section 3.2 actually, we were able to next start taking a graph like this one and plotting its derivative right down below. The refresher on how this worked was, we go to any point, say this one, imagine building the tangent line, that's that dashed line there, and thinking about what the slope would be. This would have a slope that's negative, but the derivative is equal to the slope of that tangent line through here in big, bold, yellow words here. So because we have a negative value, our graph starts below the x-axis until it hits this. This is our graph of the derivative. That occurred here, right where there was a horizontal tangent line, and we're going to call that area a local minimum. Then the curve starts increasing, so the derivative is above the x-axis, but it rounds off here. This is going to be a local maximum, and again, where the local maximum occurred is where the derivative was zero, looking at the graph. Likewise, over here, we have a zero derivative and a local minimum. So that's kind of the idea of how section 4.1 goes. We're just using the idea of local minimums and local maximums can sometimes be found where the derivative was zero itself. Well, any questions about that at the moment, folks? Okay, let's keep this kind of picture in our mind's eye and let's take a look at what's coming up next. First thing we really have to do is just give a formal definition of what we mean by minimum and maximums values. And actually, that's kind of tricky. We'll go a little bit slow in section 4.1 because the first bit we need to talk about is absolute maximums and absolute minimums. And then we turn the picture all around to talk about local minimums and local maximums. This is actually a much harder topic right here, so we'll take our time with this one. In fact, I even threw a caution on there. That's how you know it's probably a little bit trickier. But here's where it all starts. We're taking a look at the definitions of absolute minimum and then local minimums, and likewise for the maximums. And here's just a selection of different functions. I mean, if you look at this part, the y equals, it seems as though we're looking at the same exact function on every single one of them. But that's not actually true. To define a function, you really need two things. You need a formula to say what are your inputs, give your outputs, how it should work. So that's the formula. But you also need a domain. And because all the domains are different here, you truly have 4 different functions, all very similar, but different domains on each one. Nonetheless, this is kind of a nice warm-up picture. On our very first graph right here, we're going to state the absolute maximum and minimum values for each of the function. Let's start with, say, minimum. Let's do this one first. An absolute minimum is the lowest point on the graph, which means it has to satisfy this inequality. So if we look at our first graph over here, clearly that's got to be the minimum, right? Right at this location. So let's say, state the absolute minimum, maximum minimum values. We would say f at 0 equals 0 is the absolute min. I'll write ABS for absolute and min for minimum. Same for maximum. So we have an absolute minimum right here, and the way this again works is we pick any other value x, on the domain, can be any real number whatsoever, say it's this value. This would be the output, f of x. And because f of x is larger than every other output over here, whether it's larger than f of 0, we'll say that f of 0 is the absolute min. But now that we're looking at this graph, it does have a bit of a problem. If the domain is all real numbers, any volunteers for what we should say about the absolute maximum on this graph? Oh, sorry, just saw the chat. Good call, Dana. Infinity is a good way to say it, but it's just another way of saying there really isn't a maximum. They just get higher and higher and higher, so there's no actual number you can put down. So infinity is a great way to think about it. In this kind of problem, if we're doing it as, say, a WebAssign homework problem, best way to probably respond is just to say no absolute max, since the values always get larger. That's a E right there. So we could put some arrowheads on here. I oftentimes do that when we're sketching these kind of graphs, just to convey it's going up forever in that direction and same in that direction. So this graph has no absolute maximum value whatsoever. Any questions so far, folks, on our first one down right here? Okay, well, example one is all about comparing what happens as you make small changes. So here we have a domain which is all real numbers from negative infinity to infinity. And then we convert to this domain. The brackets are saying that 0 is part of the domain and so is 2. And just for shorthand, we often call this a closed set or a closed interval. Let's you say it that way. Our author usually says closed interval of real numbers. So from 0 to 2, we have a closed interval. And closed intervals play a super special role. For example, we still have the absolute minimum at 0. So it's this value. Let's just say it again. F of 0 equals 0 is the absolute minimum. But now this time we also have an absolute maximum. This is tricky though. The absolute maximum is not 2. That's kind of unfortunate. The thought is 2 is like the address that says put in this input of 2, you come up here, get a function value, and over here, whatever this value comes out is, that's the actual maximum value. So this is kind of tricky. When it says maximum value of f, we mean the y-axis output. So we don't mean the input 2, we mean what happens when you put 2 inside of y equals x squared, and we get a 4 out. So we get this value, a little dash line just for emphasis, and get 4. And we can now say f of 2 equals 4 is the absolute max. Well, that's 2 down so far, but I'd say the bigger emphasis this time is oftentimes in the homework, you're being asked for the maximum value of f or the minimum value of f, and it's always going to be these values. Whatever the output is, sure, it's not a big deal on this first one, because if you gave it 0, that's the same input and the output. But suddenly it's a big deal on this one right here where the red dot is, because if we input 2 into the system, you're partially right, but we wanted the output value for the maximum, the output being 4. Well, any questions, folks, with that second graph? Okay, let's keep on going forward then. So we started with the entire real number line. This is sometimes referred to as an open set. More importantly, this one is a closed interval or a closed set. And then this one's a little bit weird. we have an open on the left side where the 0 is. This is telling us we can take any positive number except 0. For example, 0.1 is in that set, 0.001 is in that set, 0.000001 is in that set, but not 0 itself. However, on the upper end, 2 is in that set, so we don't have the same weird game where we're taking smaller and smaller numbers, excluding the lower boundary value of 0 in that case. So this set is pretty weird, and you can double check this because it almost sounds made up. It's half open, half closed. So oftentimes what the topologists call this is a Clopin set or interval. So Clopin meaning half open, half closed. So really pretty weird. And it has all sorts of weird consequences. First consequence, let's think about the absolute minimum on this one. Any volunteers for what we should say for what is the absolute minimum? Thanks for the chat. Emily says 4. Turns out it's not 4 on this one, or unless you're talking about the absolute maximum. Sorry, I think that's what you're referring to. Yes, absolutely. On this one, because of the closed right here at 2, it means you can really put a 2 inside the function. You go over here, you get your output of 4. So let's put this on the graph. Here's a 4, and we can say f of 2 equals 4 is the absolute max. But now there's some extra interesting thing happening here when we're thinking about the minimum. It's going to be tied in with the fact that we don't actually have 0 in the domain, so you can't plug 0 inside the function and get 0 any longer. Anyone see what we should say about the absolute minimum then in that case? Oh, here comes a couple chats, awesome. It turns out it wouldn't be a 0.01 because, again, the thing that's really weird about this is we could play this weird little number game that starts to go on forever. Let's pull up a calculator just to illustrate. Again, this problem right here is just another way to emphasize maximum minimum values. They seem not so bad on paper, but they really get tricky. And what's making it tricky is messing with the domain of that function. You have just an ordinary function, not as bad. But this is now exceedingly tricky with that parenthesis right around 0. So let me actually get into the calculator here. Let's define a function, f of x equals x squared. And let's work with this domain right here. So let's put that in. We're going from 0 less than x less than or equal to 2. There we go. So strict less than right here because of the 0 with the open parenthesis, but we have less than or equals on the 2 because of the bracket. So that's what the bracket is trying to say. We're including the 2 on this one. And now, well, that means if we are always bigger than 0, we might plug in, say, f of 0.1 would give us a value. So we have a minimum 0.01, or excuse me, I shouldn't have said minimum. We have a small value of 0.01 so far. But the trouble now is that's not the smallest we can go. 0.01 is still in the domain. We get a next minimum of it's not a minimum, we get a next smaller value of 0.0001. And again, this goes forever. We can't ever call this a minimum because we can keep on getting closer and closer to 0 on this left end of the domain. Let's add another 0 to illustrate. And the output values, they keep getting smaller and smaller. We can say at the limit, it's a limit of 0, but that's not what we're doing here. There's no limiting operator. And that means if we can keep on getting smaller numbers for all of time, there is no minimum any longer on this function. So it's kind of like the very first one having no absolute maximum, just a lot trickier now because of the issue with the domain. So we'll say here on this one, there is no absolute minimum value. So this would be, again, much like the first graph when there is no absolute max. Well, does that make sense to folks on the issue here with no minimum? Okay, so moving down the line, here's our next one to take on. So this interval is, again, a little bit different. We would refer to this one as an open interval. And notice kind of the effect of what's going on. When the last graph was open on the left, there's a hole on the actual graph of the function, but there was no hole up here because of this bracket. But now with both ends open, no brackets, we're excluding both 0 and 2. We have a hole on the lower end, a hole on the upper end. And so that means on this graph, it's kind of similar to the last one, but we get to say there is no extreme values of f. When we go to say there's no extreme values of f, what we mean is there's no absolute maximum, there's no absolute minimum whatsoever. So that's what's happening and playing out on this graph right here. Well, any last questions, folks, on looking at those 4 different kinds of situations? Okay, well, with this information so far, we're going to now extend on the idea of an absolute maximum and an absolute minimum and start talking about local maximums, local minimums. So that's essentially a picture like we were showing in section 3.2, right at this location where the red dot is. Nearby, if we don't go too far to the left or too far to the right, this is a local minimum. Likewise, if we're up here, then nearby this area, if we don't go too far to the left where there are higher values, just locally around here, we have a local maximum, and then once again, a local minimum. So pictorially, that's what those things look like. But actually working out the problems, it's a little bit more technical, unfortunately, because of small issues with domain. And there are similar issues as what we see over here. Tiny changes on your domain have really big ramifications on what you can say for an absolute maximum and absolute minimum. So let's turn to that next set. And here's our definition 2. I think of this one as the tricky definition in this set of notes. And here's how it goes. We say f at c is a local maximum if we can make this inequality work for us. It's the same as the one above, but the new information is that inequality has to only work when x is near c. Likewise, a local minimum means we found a value such that f of c is smaller than f of x for x only nearby that number c right here. So now we have another problem. The way to really define local minimums and local maximums is now required for us to say, what do you even mean when you say x is nearby a number? So expanding on that a little bit further, this is the definition our book likes to give. If we say something is true near a value, say c, it means it's true on some open interval, just like those open intervals we saw above on the notes. Let's just take a quick peek. Open intervals like this one, for example, there's got to be an open interval, AB, for which C is in the inside of it. But this also means that open interval AB has to be contained within the domain of the function. Let's make just a quick comment here to say that statement. AB, as an open set, must be within the domain of the function. And this statement we're writing here in orange is what leads us to the cautionary statements down below. So because of the fact that when you say nearby C, you put an open interval centered around C, and because that interval has to be within the domain of the function, it turns out The consequence of all these definitions is that there is never a local maximum nor minimum value at the endpoints of the domain of a function. So let's maybe highlight this a little bit better. It's a true never. So no matter what happens right here on this red dot, whether it's solid or open, we can never say local maximum nor local minimum at that area. And same with this one, whether it's open or closed, we can never say there's a local max nor min at that other end, the end boundary of the domain. Well, any questions, folks, with these technical issues at the moment? Okay, I think probably, honestly, the best way to absorb what's going on in these definitions is just to try it out down below here. And because we're talking about things that are local, another really great strategy is grab a couple note cards. You want to place them around your graph and just kind of have blinders going on. I'll simulate that using, let's go and forget it can add a lot of different highlighters on this system. When Microsoft Word is up to date, they only allow you 3 pens, 3 pencils, 3 highlighters. I don't know what changed, so out of date Microsoft Word is excellent. So we're going to go step by step, and suppose we're looking around at 2. Strategy is take your note card and like this. Wipe out the function to the left and to the right, because when it talks about local values, local minimums, local maximums, this is all that matters, what's going on around 2 or nearby 2. Okay, let's undo this and start out the strategy going left to right. We'll just start at, say, 0 and pause anytime we get to somewhere interesting on the graph and say we have a local minimum or a maximum. So starting at the very far left, here's where we have a problem. There's an open interval right here at the end of the domain. That means there's no maximum or minimum right at this very end right here. So it's much like if we took a look at the graphs up above once more. This problem, there's no local maximum here either because of the open dot on the graph. So even though this number is interesting, there is no local minimum or maximum at f of 0. We don't have to say that, but just for the sake of the notes, let's start off by saying that right away. F of 0, which equals, let's just add some marks on the axis so we're not counting each and every time. So f of 0, now that we've done that, we have a big problem. F of 0 is undefined. This is good to say here. It's undefined because of that open dot, which means no local min nor max. So right out of the gate, there's a trick question on this. But moving on beyond that, it gets a little bit nicer to take a look at minimums and maximums. Any questions first, folks, on that left end boundary of the domain? Okay, well, as we move through the graph, we have a nice continuous curve until we get to this, the removable discontinuity. So something interesting may be happening around 2, but because we're only concerned about local values, we put in an open interval around AB containing the number C, which is a 2 this time. I'll visualize the open interval just by doing some highlighting. So here's our interval. It looks like it goes from about 1.5 to 2.5, and it means we're only looking at this part of the graph, the part right above it. Everything else is now a gigantic distraction, so let's just wipe it out. And we're interested in that value right there. Any volunteers from the class, would you call that value a local minimum or a local maximum? Good call, Jamie. We have a local minimum right here. What makes that a local minimum is we write down f of 2 equals 2. This value of 2 is less than all the other values here on the left end and all the values here on the right end, and that's what makes it a local minimum. So f of 2 equals 2 is local. Oftentimes I'll write LOC for local and min. So that's one down. Let's reveal the function and just move on down to the rest. So we had something interesting happening at 2. Let me just fill out the rest of these numbers. It's kind of annoying sometimes having to count those off each and every time. So at 2, nothing interesting, or excuse me, we have a local minimum. Then as we move over, we have something more interesting right around here at 3. Let's throw a dot in. So if we're locally around here on 3, this is the only part of the curve that matters. The rest of this is now just officially gone. And that's not so bad to analyze. Right here, we have the curve coming up and around in this kind of way. Derivative would be 0 in this location, where the blue dot is, and that would be a local maximum. Looks like it takes a value 4, so we'll say f of 3 equals 4 is a local max. Let me just define that shorthand real quick. We'll often say LOC to mean local. So we have a local max in this location, not too hard to see because of the nice shape the curve takes, nothing crazy going on. Then moving on even further, let's see where it's going on a little bit further. It looks like another interesting thing is happening right here at 4, right on that spot. But at this point, I don't know if we need the graphs as much, or the blinders, or the go cards if you're using them. Right here, it looks like 4 is definitely going to be a local minimum. So let's say f of 4 equals 4 is a local min. But it's actually even a little bit more than that. Even though we didn't have to say it in these instructions, this value of f of 4 equals 4, let me fix that real quick here. That's really bad function notation. What I should have said is f of 4, which takes the height of 1, there we go, that fixes it, is a local maximum. So, lost my train of thought there. Oh, also, that value is a little bit more special. We can say f of 4 equals 1 is also an absolute max. We didn't have to say that this problem again, mostly just for the sake of the notes. Jamie asks, how will we know how many local values are to provide on exam? Is it based off all the x values? It'd be based off all the x values that return something special, for example. For example, here on 5, on this part of the curve, we don't have a local minimum or maximum, but we do at 6. So we just have to mention each time the curve kind of peaks out or dips out, or has this kind of feature right here. So those would be the values we'd be going after. So like we were saying, looks like nothing is interesting happening at 5 because curve looks like this. Once you get over to 6, something is happening. Right by 6, we have a peak on the graph, and we can say there, that would be a local maximum. So let me write this out carefully this time. F of 6, which is equal to the height of the curve when x is 6, looks like it's at height 3, is a local max. Well, any questions so far, folks? Getting up to this part of the process? That's a good question. Well, let me fix my wording right here. F of 4 equals 1. I said it was an absolute max. I think I was losing my train of thought here. I must have not drank enough coffee before class. Let me fix that. That should have said min. And what makes this value right here an absolute minimum is it's the lowest part of the graph for every function value that occurred. But how will we observe an absolute maximum? Actually, this graph is extremely tricky for finding that. So let's imagine first that it wasn't so bad. Let's imagine, for example, that this was filled in right here. Then that would make that location the absolute maximum because this dot, height at 5, is the highest height that ever occurs on this entire graph. So that's what makes it an absolute maximum. And that's what's making this point down below here an absolute minimum. Does that make sense, Dana, on finding the absolute max? Oh, sorry, didn't mean to scroll. Okay, well, getting back to that discussion on the absolute max, we return the graph back to this situation. Now suddenly, let's add this to the notes. Because of that open dot here, there is no absolute max on this particular graph. It would have to be filled in to get that absolute maximum, much like if we had, say, these graphs again. This one had an absolute maximum because the function value at 2 actually gave us a 4 back. But this one loses the absolute maximum because f at 0 is not 5. It comes out as undefined. So again, this is what graph here has lots of weird particular issues. But going through the process, we found, let's see, just to remind ourselves, this was the local minimum at 2. We had a local maximum here at 4, local minimum at 1, and now we just found a local maximum here at 6. And Dana asks, what makes the filled dot not an end of the graph, like in the caution? So what would make it not an endpoint of the graph would be if the open dot is in the middle here versus the very far left or the very far right. Dan asks, how is it that because it's filled in, it becomes the absolute max? Let's return to that filled in graph right here. So if we plug that in, then from right here, we can now say f of 0 equals 5, only because we plugged in the value. And then this would be an absolute max because nowhere else on the graph does a height of 5 ever occur. So looking at the rest of the graph, these are the function values. Now they're around 4, getting a little closer to 3, jumps down to a 2, increases back up to 4, but from then and the rest of the time, function values are always below 5. That's what would make this one an absolute max. And Dennis says, is that still an endpoint, still not an endpoint of the domain? Well, if it filled in right here, it would be an endpoint of the domain. But the caution's saying there's never a local or minimum value. It's not referring to the absolute maximums or minimum values in the caution, only the local ones. Does that make sense there about the issues with the boundaries of the domain? Yeah, absolutely. Thanks for asking those questions. Again, this is what makes it all extremely tricky. And maybe a better way to have started off this problem would have been to go like this. In example 2, the domain is, oh, and I already made a mistake. The domain starts out as an open parenthesis at 0, only because that dot's not filled in. And then from then on out, even at 2, we have a function value because of that dot. We have no problems, and we go all the way to 7 with a closed bracket. So 0 is the left endpoint. There could be no local minimums, no local maximums. 7 is the right endpoint, and notice how tricky that is. It's tempting to call that a local minimum, but we can't. It's at the endpoint of the domain. Let's put down on the notes just to emphasize that. 7 is the right endpoint. Of the domain, and that means f of 7 is not a local min, only because of being at the endpoint of the domain. Again, it's not a bad idea to rehash what goes wrong. Well, for that to really be a local minimum, we'd have to put an open set AB containing the value C. It's 7 in this problem, but AB must be within the domain of the function. So if we try to do that, highlight numbers around 7, we can go to the left, but we have to push into the right. That's where it all goes wrong. The domain ends right here. We actually can't put in an open set that includes 7 unless the curve were to do something like this. It has to keep on going further, for example, but it can't end right there, or else there's no open set we can actually contain around 7 itself. So that's the full picture on this one. We only have 4 different values that are local minimums or local maximums, these 4 right here. Any questions or comments at all, folks, on getting through these? Okay, really, there's a lot more we can say about this. And it's a good idea to kind of go slow with these ideas because they are tricky enough all on their own. So before we push on to the next topic down below right here, extreme value theorem, let's take another look at this graph and just make some comments. So let me go here and highlight. And let's put it right here, just on a new page. We'll come back to this one. Sorry, let me just fix how things are scrolling. Okay, so back to this graph, just to look at it a little bit more. Let's call this section just say further comments. And the comments we can make here are really so far about when we could find a local minimum or a local maximum. It happened in 4 different places. So first, let's take a look at what happened here at 2. Here we can say f of 2, let's say it this way, f prime of 2 does not exist due to the discontinuity. So if you have a discontinuous graph, like we do right here, that means you can't even take the derivative. So we said f prime of 2 doesn't exist. But it does exist up here, right at 3. We have a horizontal tangent line, which means the derivative would be 0. So we can say here, f prime of 3 equals 0. Next one down below, the curve comes down in a really sharp corner. Whenever we have a corner like that, the derivative also doesn't exist. It's got to be a smooth curve like we see right here for differentiability to work. So right down at 4, we can say f prime at 4 does not exist due to the corner. But coming up above, right here at 6, we found a local maximum, and that derivative did exist. We can say f prime at 6 equals 0. So this is the observation. Each time you find a local minimum or a local maximum on these kinds of graphs, one thing that's going to happen is either your derivative just didn't exist in the first place, or the derivative does exist and it equals 0. So these are the kinds of places we want to start looking for where we can find local minimums, local maximums, those kinds of features of the graph. And it's kind of really just a callback to this kind of graph right here, where once again, there's a local maximum in this location, which means the derivative is 0, and same for the 2 local minimums here and here. We have a 0 derivative in this location and in that location. But any other questions, folks, with just those further on comments here? Okay, so far we know lots of really weird things can happen to our graphs if we allow just annual graph to work for us. But this theorem here says if we look for specific kinds of graphs where the function is continuous on a closed interval from A to B, then a lot of these weird issues we are seeing on these graphs totally go away. So if we have continuity on a closed interval from A to B, then this extreme value theorem tells us f will attain its maximum value f of c and its absolute minimum value f at d at some numbers c and d in that domain. So that's kind of impressive. This is now a guarantee. All you need is 2 things, continuity and the closed interval. Now let's draw out some pictures just to see how that would work. So we have let me use a slightly different pen. Let's say we have a function, y equals f of x, and it is continuous. let's give it some definite numbers. Let's say we go from 1 to 5. Let's attempt to graph this function. So we gave it these two conditions: continuity on a closed interval from 1 to 5. Now the problem is going to go on and say, f attains an absolute maximum and an absolute minimum somewhere, some points, some numbers C and D in the domain. So that's the guarantee of this statement. And kind of the challenge here, just for fun, is try to draw a curve where that doesn't happen, where maybe one or both is missing. You might make your curve, say, do something like this. Let's start right at 1 with a solid dot. It's got to end somewhere at 5 with another solid dot. And so we make it just go up like this. We did it, folks. This is now the absolute maximum right at that height. The absolute minimum would be at that height. So you might decide, well, what can we do to be more clever and make this not happen? You might decide to make your curve, say, go down. But we can't put a vertical asymptote on there because we would lose continuity. And we can't make it keep on going down forever like that because we have to end at some solid dot. So no matter how much we fight, maybe our curve looks like this. Same issue. The only thing that changed is on the left now is the absolute maximum, and the right is the absolute minimum. So there's the absolute max and absolute min. So this turns into a really powerful theorem in this kind of sense because it can allow us to find absolute maximums, absolute minimums. Any questions, folks, with that extreme value theorem so far? Okay, so we're starting to collect a lot of interesting tools, and a lot of the things that we're gathering are kind of related to, once again, these ideas right here. Turns out it's just really interesting if you're looking for maximum minimums, whether they're absolute or local, you want to find out where is your derivative 0 and when does the derivative just fail to exist in the first place. So those become interesting values, and they're now further supported with this theorem, theorem 4, Fermat's theorem. It says if f has a local maximum or a minimum at value c, and if the derivative also exists, it turns out the derivative has to be 0. That's an impressive statement because it gives us a place to start looking. But Fermat's theorem is also dangerous because just because the derivative is 0 does not in any way actually guarantee there will be a local minimum or maximum whatsoever. That's a bit of a surprise, and the trouble is the logic has to go a certain direction, left to right. So the only way to use Fermat's theorem is you have to know that there's already a local minimum and maximum. You have to know that the derivative exists, and then you are given a guarantee the derivative will be 0 in that case. Let's give this a try on just this example function. But first, any questions, folks, with the statement of this theorem? Okay, the part of this theorem I want to focus on is this right here, the derivative coming out at 0. Let's take a look at that function. If we differentiate it, we would just be using the power rule. So 5/3 comes down. X is to now the power of 2/3. And well, we have a derivative f prime of x, and we want to solve this equation. We set it equal to 0. And we're looking for the value of x that makes this a true statement. Over here, this is not too bad to solve. You can multiply both sides by the reciprocal of that fraction, and you just get x to the power 2/3 equals 0. Right-hand side just multiplies your reciprocal, wipes it out once again. Now the only way this equation is true is if x equals 0. So we can now say f prime at 0 equals 0. So we matched this part of Fermat's theorem, but it turns out, if we look at this graph really carefully, there is no local min nor max. Again, that's a big surprise. The trouble is, Fermat's theorem can't be reverse engineered in the sense that if you start with the right-hand side, the logic doesn't reverse and then suddenly guarantee you have a local maximum or a minimum. That's kind of unfortunate. And let's see it working with a graph right here. Let's wipe out these. Our function is that y equals, if I can type it in right, y equals x to power 5/3. Now, the interesting value is at 0 because that's where the derivative itself comes out as a 0, which makes sense. There is a horizontal tangent line right here, but also observe there's truly no minimum or maximum because this curve is always increasing. It just so happens right where it gets to that spot, the horizontal line's tangent, it's as if the particle is at rest for one moment of time, but then it just starts going up and up, once again, for no maximum. So let's plug this in just as a punchline to our problem right here. This is y equals x to power, let's say it this way, y equals f of x, which is x to the power 5/3, and it has no local min nor max, despite the fact f prime of 0 is 0 on that graph. So in some sense, it feels like Fermat's theorem is kind of useless in a way, but it's still a fantastic theorem. The idea is still that even though knowing the derivative is 0 is not going to guarantee we found a local minimum nor a local maximum, it's just the place we start looking. Because we observe when we do find local minimums and maximums, two things always happen. The derivative is either 0 or just didn't exist. So again, that means we start looking for those values, hunting for local minimums and maximums, whenever the derivative is 0 or it does not exist. And that gets us to our major topic, the notion of a critical number. So definition 5 says, critical number of a function is a number C in the domain such that either the derivative is 0, like Fermat's theorem, or the derivative just doesn't even exist. So we like critical numbers because if we're hunting for local minimums or maximums, the first you're going to consider. Sorry, question over in Zoom? I think I missed a question. Okay, well, practicing this out, what we're going to do is in example 3, just figure out how to get those critical numbers. Then, in our final example, we're going to combine everything together. The extreme value theorem leads directly to a closed interval method. This will be our major technique on these notes and the last problems so you'll be working on in this homework set. And the closed interval method is a step-by-step guide that guarantees you'll find an absolute maximum and a minimum value. But whatever method you're looking at is what I meant to say. Step 1 is to find the critical numbers. In the later sections, we'll be looking for local minimums and maximums, and step 1 is the same. Find your critical numbers. So that means this definition here is going to start to play a really special role. What we'll be doing is grabbing these functions. Step 1 is we take their derivative. Not so bad on this one. Differentiating a polynomial will give us 3x squared to start, then minus 6. So that's our step 1, differentiate. But then if we're finding critical numbers like we're asked to in example 3, we look for ways that this might not even exist. Well, the domain of that is all real numbers, and so that's not going to be a problem on this one. Next thing we look for is, when will the derivative be equal to 0? So once we go and write a little bit more officially with an actual pen, equals 0, we're now on step 2. Let's say for step 2, solve f prime of x equals 0 by whichever method we can manage. This one's not too bad to make happen. There's a couple good strategies. You could isolate the x squared portion and then just take the square root. Let's go with that route. Add 6 to both sides, and we have 3x squared. Divide by both sides by 3. We have x squared equals 2. Next step is to take the square root of both sides, and we get x equals plus or minus root 2. At this stage, we're done. If we want to be a little bit more specific, we can say the critical numbers. I'll often stay, instead of critical, just crit as a shorthand. So the critical numbers are root 2, negative root 2. So that suggests to us, those are the first places we're going to look if we're trying to find maximum minimum values of that cubic polynomial. Any questions at all, folks, on coming up with our first set of critical numbers? Okay, I guess our step-by-step process isn't too involved. It's just take the derivative. Let's just say that on step 1, compute f prime of x, and then the second step, set it to 0 and solve. That's basically going to be like our mantra in chapter 4. It turns out some of the best applications of the derivative in calculus is optimization, maximization, or minimization. And whenever we're optimizing, this is step 1, compute f prime of x. Step 2, set it equal to 0. So we'll be doing that tons and tons in chapter 4. And we'll try it again in part B. This one is quotient rule, so it looks like a little bit more exciting. And same steps as always. First thing we do is just differentiate the function f. It is a quotient rule, so let's take our time with it and practice it as kind of a review problem. F prime of x goes this way. We take x minus 5 and differentiate it. Multiply it by x plus 7 minus x minus 5, and then differentiate the denominator. Put that in as x plus 7 prime. If you're following these along, but you put just a 1 right here and a 1 right here, I'd say it's a good shorthand. Differentiate as you go. But it's still a pretty new process, so we're taking our time with it as well. We take the denominator, x plus 7, and just square it. So we're just about done. On the left over here, that derivative is just a 1. I'll put that 1 there just as a paper trail to say we didn't forget to calculate it. So 1 times x plus 7 minus x minus 5. This derivative over here is also 1, so it's times 1 over here. All over x plus 7 squared. Now, each time we did the quotient rule, we actually took the time to simplify these way down. And that's because we were thinking about this kind of work, actually. Let's fully simplify the numerator. It's going to be x plus 7. Distribute the negative sign through to get minus x. Plus 5. Divide the whole thing by x plus 7 squared. And here's our last step, just to simplify. The numerator is now 12. And the denominator is x plus 7 squared. Well, we did it, folks. That's our full derivative right here. Next thing we're going to look for is critical numbers. And when we go to do that, one thing we're trying to find is, where would this derivative not exist? It's a little bit easier, or excuse me, it's a little bit less tricky than this one because this derivative always exists for any choice of x. But down below here, there's one exception. You cannot plug negative 7 into that denominator, which means f prime of negative 7 does not exist. We might be thinking along the lines of, well, the critical number definition says we should be looking for these where the derivative doesn't exist. Let's take a look at that definition just to be really sure on its wording. I think this is a tricky enough problem to want to do that. So a critical number is going to occur whenever the derivative is 0 or the derivative does not exist. And the number c it's referring to right here is a number c in the domain of the function itself. So coming back over here, we can also say, well, domain of F is from negative infinity to -7, union from -7 to positive infinity. The reason it takes on this domain is over here, you can't plug in a -7 either. You'd be dividing by 0. So this now tells us -7 is not in the domain of F. So for that to be a real critical number, we had to have C inside the domain of F. And now we get to say, this implies C equals -7 is not a critical number. Those deserve exclamation marks because, again, I think this is pretty tricky and subtle. If you're really looking at this carefully, you notice derivative doesn't exist at -7, still isn't a critical number because from up here, you could never plug in -7 in the very first place. So last thing we're going to look at is when the derivative is 0. But any questions, folks, about this issue here? Okay, so last step on this problem, we need to find out where this derivative, so following the equalities, all of this is f prime of x, we need to know when is that 0. So last thing we do on these notes is we write f prime of x equals 0. This implies that 12 over x plus 7 squared equals 0. Now that's a really special equation because the only way an equation like this is actually true is if the numerator itself results in a 0. The reason is you can immediately just multiply the right-hand side of this equation by x plus 7 squared. Same on the left-hand side. Causes a cancellation going this way. And now you have an equation that goes 12 equals 0. Well, there's no solution to that. And so our conclusion is f has no critical numbers, making this a pretty wild function after all. So that's one thing that's pretty interesting about functions. Sometimes they have critical numbers, other times they have no critical numbers whatsoever. And this is one of those cases. Well, any questions at all, folks, with the rundown on this one? Okay, as far as the homework goes on the WebAssign, there's a little bit of problems looking at graphs like we did at the start of the notes, but not too heavy in this direction. The bigger takeaway on these notes, I would say, is knowing how to compute these critical numbers and knowing the role they play. That way, once we go to this topic, this is the even bigger takeaway, the closed interval method. So if you're studying this section for the purposes of, say, exam 3 or even the final exam, you need to know how to do the critical numbers. I'm not going to give you a bunch of tricky graphs. That was more to just get the conversation starting on what is a local min and local max. So you'll know how to do critical numbers, know how to do the closed interval method, and then you'll be in great shape. So here's how the closed interval method works. We want to find the absolute maximum and absolute minimum values of some continuous function f. But notice it says the function is going to be continuous on a closed interval from a to b. Probably have to undo that highlighting so not everything is highlighted. But what that is saying now is this part of the theorem is in play. We can now use the extreme value theorem. Extreme value theorem gives a guarantee of an absolute maximum and an absolute minimum, but it doesn't say how to find it. It just tells you they're there. They exist somehow, some way you can get them. The closed interval method is what's telling you how to actually find them in a nicely packaged step-by-step process. So that's the idea. I'll leave this highlighted here. Well, we should take that off. But this is the idea. If we have continuity on the closed set, we're really just using the extreme value theorem in a step-by-step way. First thing we need to find is the critical numbers. And then to get the absolute maximum minimum, we evaluate the function at the endpoints and at those critical numbers. The largest value is the absolute maximum, and the smallest value would be the absolute minimum. So that's how it all connects. Step one for almost all the problems in chapter 4 is always the same. Find the critical numbers of f, and notice how the way it's conveyed. It's an open set AB. So down over here, step one, find the critical numbers in the open set, 1/2 up to 2. The reason this turns into an open set is because in step 2, we're already going to evaluate the function at 1/2 and at 2. So step 1 is just telling us only look for the critical numbers within the inside of the domain, not at the boundary points. We'll look at that later. So that means step 1 is doing exactly what we did on the very last problem. We have to take this and just differentiate it. So let's give that a try. F prime of x will be first the derivative of x, turning into a 1, minus, here's our last section into play. The derivative of the natural log of x is just a 1 over x. So we're getting along our steps on this. After you calculate the first derivative to get the critical numbers, you take this step. We're setting the whole equation equal to 0 and solving. So now that we're solving this equation right here, lots of different things you might do. Let's add 1 over x to both sides. We'll get 1 equals 1 over x. Next step, just multiply both sides by x. And x equals 1. We want to make a conclusion. We can now say 1 is the critical number of f. You should also do a boundary check, or excuse me, a domain check. 1 needs to be within the open set from 1/2 to 2, and yeah, that really is. That's a good check to make because it's easy to get values like these, which could be outside of your domain, so always double check. So that's the entirety of step 1, and step 2 says, find the values of f at the endpoints of the interval and the critical numbers. We only produced 1, but these are the endpoints of the interval, 1/2 and 2. Any questions at all, folks, before we move on to that step 2? Okay, let's make that happen. So now step 2 is to do this. Find the values of f at the endpoints. So it's again referring to 1/2 and 2. So we need to calculate f at 1/2, f at 2. Then it says find the values of f at the endpoints and at the critical numbers. Over here we said 1 is a critical number of f. So we need to calculate f at 1 next. So 3 computations. We have to give the exact values, so sometimes it's a good idea to just plug these into the function first, and then put them in the calculator if need be. So f at 1/2, and notice the danger here. When it says f at 1/2, it's referring to the original function f at this point. It's not talking about the derivative. So one thing that's a good thing to do on your notes, just as a good protection, is whenever you're working with f, start off by writing f equals, and every time you're working with f prime, start off with f prime equals. That way the results don't get too jumbled up on your notebook, and you can tell where you're getting your values out. There'll be problems where we have f, f prime, and f double prime. Without labeling what's what, everything gets totally jumbled up. So a big part of the closed interval method is actually just organization. So with that idea, actually, let's just put some temporary highlighting in this way. We're plugging these values into the original function f. So 1/2 goes here, minus natural log 1/2. I want to calculate to approximate that, but let's move on next to f at 2. That would turn into 2 minus natural log 2. Finally, throw in a 1, and we'll get a 1 minus natural log 1. Actually, that's the only one I could do exactly, because natural log 1 results in 0. So we have a 1 on that one. And we'll do a calculator approximation on the rest of them. So grab out your favorite calculator. We need, going top down, 1/2 minus natural log 1/2. We don't need a lot of decimals for approximation. We just need to know the relative size of things. So let's call this 1.19. And last one. This time it's 2 minus natural log 2. That one comes out as a 1.31 after approximating. And that means we're ready for our conclusions. This is really all we need now. So here's our step 4. Let's call step 4 conclusions, since that's effectively what it is. Or excuse me, I skipped a step, didn't I? That would have been step 3. Sorry, I guess counting is a little bit hard today. So step 3 says the largest value that we made in step 2 is the absolute maximum. So let's see. That would have been this. And the smallest value is the absolute minimum. So absolute minimum is this one. Notice how I highlighted. WebAssign is more often than not going to want the actual exact figure. So when we say absolute maximum, we're referring to this right here. Definitely don't say the 2. That's not the maximum at all. That's just the input that takes you to the maximum. So our conclusion will go like this. 2 minus natural log 2 is the absolute max. 1 is the absolute minimum. So looks like we're done with the problem, but it's not a bad idea when you're learning these the first time, doing them in WebAssign or doing them as quizzes, to use a little bit of extra technology just to see, did this even work? Because it's a pretty interesting method with lots of different results all tied together. So let's put this into a graph and just see if it even seems plausible that those are the right values. But any questions at all, folks, with the total process? Okay, let me just put this in. F of x is x minus natural log x. You always want more than the function because this is about the domain as well. So we're going from 1/2 to 2. So we'll go 1/2 less than or equals x, less than or equals 2. Oh, sorry, it looks like I missed a chat there. Dennis says, is the absolute max expressed as that whole term, the whole absolute minimum should be calculated? Oh, so yes, it should be this whole value right here. It's approximately 1.31, but that's just an approximation. The exact absolute maximum is 2 minus natural log 2 right in that form. Is that what you were asking about there, Dana? Well, the minimum wasn't really approximated. This is its exact value. And if we did give this value right here, that would be correct as well. It just so happens that 1 minus natural log 1 simplifies to an exact value of exactly 1 on this problem. But you know what? That's a good comment to make, just to be specific. We're always grabbing these values right here, but if one of them simplifies in a way that gives us the exact value still, we're always grabbing these values right here, really. So we're giving exact values for both the maximum and the minimum. And this value is not an approximation. This one turns out to be dead on accurate. But let me put this little approximation symbol. The ones here and here, those were the actual approximations. Yes, that's correct. This is the only exact value here, the 1. Other questions at the moment? Okay, so last thing to do, just to double check, let's see how we did. We said that if we plug in one, we get a one out, and even more, that one is an absolute minimum. And here it is on the graph. Looking about right, it is a minimum, it's both local, but what makes it an absolute minimum, it's also the lowest point on the graph as well. Then we said 2 minus natural log 2 is the absolute maximum. The way we get there is you plug in a 2. So that should be the value way out here. Looking at the approximation, it's 1.30685. Let me see if I can get that to stay. No, it doesn't want to. And that's the same approximation that we're giving down below, just rounded to 1.31. So that really was an absolute maximum right up here, but its exact figure was just 2 minus natural log 2. So it's kind of neat to see the process actually working out. It doesn't always work out. The closed interval method will only work if you have a function that is continuous, and it's continuous on a closed interval. So those are the two required ingredients for this kind of process. But with what we'll do next time, let me just try to actually get this out of here. There we go. When we come back on Wednesday's class, we're just going to do it all over again. I feel like at least 2 examples is a good idea. So here's part B of the same example 4. We'll find the absolute maximum minimum of this function right here. And let me zoom in a bit on it. This one's a little bit nastier because it's a product rule with a chain rule. So this is like the worst case practice problem. And this one above, kind of more of a routine example that you would see on quizzes and exams. Well, this one is like a 12-minute problem, I'd say. So this will be our stopping point for today. Any last questions or comments at all, folks, before we call today? Okay, well, have a wonderful afternoon, everyone. When we come back on Wednesday, we'll finish off these notes and then move into looking at applications of the derivative even further. More of this kind of stuff. Take care, folks.